Alright, so hello and welcome. Here we are, another problem. Take a moment here to make sure the audio is working, live stream's working. Decided to keep going. Hello. Decided to keep going because I was kind of bored. Kind of bored and wanted to finish the work here. So let's do it. Moving stones until consecutive 2. Let's see how we do. There are some stones in different positions on the x-axis. You are given an integer array stones. The position of the stones. Call a stone an endpoint stone if it has the smallest or largest position. In one move, you pick up an endpoint stone and move it to an unoccupied position so that it's no longer an endpoint stone. Excuse me, particularly if the stones are at, say, stones 1, 2, 5, you cannot move the endpoint stone at position 5, since moving it to any position, such as 0 or 3, will still keep the stone as an endpoint stone. So you can move it between 1 and... Oh, no, you can't. Oh yeah, you can't move 5. Okay. Game ends when you cannot make any more moves. The stones are in 3 consecutive positions, but you can move a 1. You can move 1 between 2, 3, and 5, and then move 2 between 3, 4, and 5. Okay. Return an integer. Game ends. You can't make any more moves. Okay. Return integer array answer of length 2, where answer 0 is the minimum number of moves you can play, and answer 1 is the maximum number of moves you can play. Whoa. Okay, you want to get the minimum and the maximum number of moves. Alright, so minimum is 1, maximum is 2. So 7, 4, and 9. Probably should just short sort the stones first. Only 10,000 of them, yeah. All the values are unique, between 1 and a billion. Not a lot of submissions in this one. Whoa, very high acceptance rate though. A lot of downvotes. Yeah, people didn't like this one, huh? Are we doing solution? Yeah, okay. Yeah, you could use this. I don't know. I don't know what to say about this one. Alright, well, I don't know. The minimum number, let's do the minimum number of moves. Probably a dynamic programming solution of some kind is the way to go. So let's try the minimum number of moves. That would be probably, you have to move an endpoint somewhere. 7 could be moved between 4 and 9. 9 could be moved between 4 and 7. Those are the only 2 options. If you move 7, now you have 4, maybe 5, 6, 7, 8, 9. Probably would want to move this between 4 and 9, and basically the game ends when the numbers are consecutive. So to have the minimum number of moves, each move should bring, basically consider, I know what to do. There's a difference in how far away the numbers are from each other, right? The elements. So 4 to 7 is a difference of 3, 7 to 9 is a difference of 2. Basically, you want to maximize with each move the overall, the total number of average number. The average number, you want to maximize the average number of basically spots in between that you remove. Yeah, and with each move, you're basically just bringing your numbers closer together. So moving, excuse me, you can't move 7. Actually, it's got to be a 4 or a 9. So if you move 4, you can move it between 7 and 9, move it to 8, and that finishes it immediately. That's one move. You could do it in 2 moves. If instead of moving 4 to 8, you could move 9 between 4 and 7. Move it to 5 or 6. I don't think it matters either way. You only have one spot left, and then you could move. You have to move 1. Move 9 to 5, 4 to 6 for 2 moves. Okay. 6, 5, 4, 3, and 10. 2 and 3. So 3, 4, 5, 6, and 10. You can move 3 or 10. I would say you can't move 10 because it's still an endpoint. So your only choice is to move 3. 3, if you want the minimum number of moves, you have an options 7, 8, and 9. I would say probably your best option is 8. You can move 3 to 8. You can move 4 to 7. And you can move 5 to 9. It's 3 moves. Oh, I know what to do. Move 3 to 8, and then you can move, now 10 can be moved to 7. There you go. Yeah, that's what they said. Interesting. And then, and I said before, you could do 3 maneuvers to get the maximum. I don't know the answer to this question. It's kind of a tough one. So yeah, I don't just have to sit and think about this then. Let's try again. So x sub 0, x sub 1, x sub 2, x sub 3. Let's say for 4 stones. And we want the minimum number of moves. Okay. So you can't bring x3 closer nor x0 closer. But what you can do is you could put x1, x2, x0 between x3 and x2, and then move x0, x3 between x1, x2, x3, and x0. So long as x3 has at least 2, it's a gap between x3 and x2. So you can clear the gap between x3 and x2 in 2 moves. Just move x0 between x3 and x2, and then move x3 between x0 and x2. So you can bring those two. You can clear the gap in 2 moves. The rightmost gap. What if you have a gap between a bunch of things? What if you have like 5, 10, 15, and 20? Right? You can always move all the elements that are out of the gap into the gaps, fill the gaps. So 10, 11, 12, and 15. And then you can now make 2 maneuvers to close the final gap. So you end up with 11, 12, 13, 14, 15, and then move 15 to 11, 12, 13, 14. So you can always perform an algorithm that does reasonably well. That'll give you, it'll fill your gaps if you have them. How many gaps do you have between these elements? It's going to be, it handles the leftmost gap and the second to leftmost gap in 1 move. And then, no, so I did that wrong. So you get 5, 10, 15, 20. Go 10, 11, 15, 20. So you take care of the left gap in one move. Then you can go 11. Oh, that doesn't work, does it? No, I did that wrong. 5, 10, 15. I can move 5 to 12. So 10, 12, 15. And move 15 to 11. 10, 11, 12, 20. So that's one move. It's two moves. 1, 2. And actually, I probably want to move this. I can't move 15 like that. No, no, no. I could fill the gaps from left to right. I could just go 5 to 19. So 10, 15, 19, 20. I can go 10 to 18. 15, 18, 19, 20. And maybe better would be to do the other way around. It would be better to go 5, 10, 15, 20 to 10, 15, 16, 20, right? And then second move, to take care of the rightmost gap. Instead of going to 17, I can go 15, 16, 18, 20. And then finally move one back to go to 15, 16, 17, 18. So four moves. Yeah, so I think I can do that in general, as long as there is a gap. As long as there's a gap between every element, I can perform a maneuver. Gives me at most n moves. Something like 4, 7, 9. Seven, 8, 9 closes everything. If there's a gap of size 2 or more on the endpoint, then I can remove that element with two moves. Move the other endpoint between one side and the other, and then move the other endpoint in there. So I can go like, for instance, 4, 7, 9. I can go 4, 9 to 5, 4, 5, 7, and then I can go 5, 6, 7. It's a pretty interesting question. How do I get the minimum number of moves? How do I get the maximum number of moves? I think I don't really have an answer for the minimum number. It's probably the first thing that I should try to think through here. I think I could use dynamic programming. So I can do I can move the left endpoint or I can move the right endpoint, one or the other. And the left endpoint could be many different positions. The right endpoint is similar kind of thing with some overlap. Just looking at different test cases, like looked at 10, 12, 14, 16, 18, where things are separated by just one space in between. Such a situation, you would you can actually do it in like n over 2 number of moves. You just move each end stone into a intermediary position. That's pretty fast. Not sure how to get that quickly though. I don't know. So the 5, 10, 15, 20, found a way to do it in 3 moves. I think before I had 4 moves, but I could do a similar kind of thing where I put 5 next to 20, put it at 18, and then I could put 10 at 17. Oh no, you could do, I think you could do this in 2 moves. You can go 5, 10, 15, 20, you can go 5 to 19, 10, 15, 19, 20, right? 1 move. And then ten could be moved. Oh, it's not 2 moves. 17, 15, 17, 19, 20. And then the third move is 17, 18, 19, 20. You could definitely do it in 3 moves. I don't know if you could do it in 2. It seems kind of impossible. No, you can't do it in 2 because there are 4. There are 4 positions, right? 16, 17, 18, 19, 11, 12, 13, 14, 6, 7, 8, 9. There are four positions between each element, and so even if you'd have to eliminate with each move, you'd have to eliminate 12 total, which means you'd have to do an average of 6 elimination of 6 different elements, which I don't think is possible. Yeah, I think you can get at most an average of 5 over 2 moves, because you can move 20 between 10 and 15, you can move 5 between 10 and 11. Both of those will remove all 4 of the elements from 4 to 5 to 9, and also from 15 to 20 when you do it. But what's left is you only eliminate 1 element between 10 and 11. Yeah. Excuse me. So I think there's a greedy algorithm is optimal here. I think basically what you want to do is go from right to left and from left to right and get the largest sum of like spaces, like this spacing, the largest sum of the spacing from right to left and left to right. And those elements are the ones that you're going to move. From right to left, it's going to be the element on the right side with the spacing on the left, and from left to right, it's the element on the left side with the spacing on the right. And what's going to happen is you're going to move these elements into open positions. That are further in. So in this case, you have a 4 and a 4 on the left, 4 on the right, and then there's also 4 spots in the middle. So you can move 20 inwards, you can move 5 inwards. Both of those are going to give you a difference of 8. And then there's obviously 1 position is removed. Each time you get 5 and 5, so now there's only 2 spots left. And you can actually reduce when I move 10, for example, or if I move 10, I can move 10 or 15. I can reduce that from 4 in the middle to 2, and then reduce that to 1. Kind of 1, because I can leave one side open. So let's say if I want to use 10, I could do 5, 10, 15, 20. Leave one slot open here next to 10, and move 20 inwards to 14, and 5 inwards to 13. Oh, no, not 14, excuse me, 13 and 12. So 5 to 12, 20 to 13, I have 10, 12, 13, 15. And now when I move 15, I lose, because it's on the right side, I lose that extra cell between 13 and 15, and I lose the cell between 10 and 12. I take care of both of those cells. And it's 3 moves, but I get 5, 5, and 2. So I think something like that's the way to go, some kind of a greedy algorithm to get the minimum number of moves. Obviously, elements that are consecutive, you don't really touch them unless they're on the end, and you might have to move them. So I don't know, we get something random like 2, 4, 1, 2, 4, 8, 20, 22, 23, 27, right? So we have 1, or no, we have 0, 1. So it's going to be 8 minus 4 plus 1 minus 2. So 8 minus 4 minus 1 is 3. 20 minus 8 minus 1 is 11. 22 is 1. To 20 is 1. 23 is 0. And 23 to 27 is 3. So how many elements do I need to move? I need to basically be rid of all of these segments except for one of them. And I think I need to go left to right to get 0, 0, 1, 3, 11. That gives me an average of 15 over 4, which is 3.75. Yeah. 3.75. And then I can also move 1, 2, 3, 4. And I can also move on the right side. There's a 3 there. So I can move 27. 1, 2, 4, 8, and 27. I can move all of those. However, there's only one element left from 20 to 22. So yeah, I don't need to do all that, I suppose. Actually, I need space to put these things. I could put 1, 2, 4, and 8 in spots on the right side. 1 and 3, so I can do 1, 2, 4, 8, 20, 22, 23, 27. I can just do 4 moves. I can do 1 to 21, 2 to 24, 4 to 25, to 26. That would give me 20, 21, 22, 23, 24, 25, 26, 27. That would be 4 moves. I don't know if I can do better than that. It's probably about as well as you can do it. Yeah, and the key here is I just want to move this spot that has 11 in it. I want to move that somewhere. If I wanted to move 20 somewhere, I'd have to move 1, 2, 3, 4 anyway. Which I could actually do in the other direction. I can go 1, 2, 3, 4, 5, 6, 7, 8 as well. Could have actually done it that way too. From right to left, that also would have been 4. Is there any situation where I don't move the 11th element, the 11 elements? No, I don't think so. From 8 to 20, it's too many things to be left over. Yeah, I think I have to move that one because I have to move either things in between 2 and 4 and 8, or I have to move 2, 4, and 8. So there's 4 spots there. So, and it's going to involve, yeah. Not sure how I could prove that 4 is the minimum though. That's kind of what I'm getting stuck on here. I'm wondering if I can use, as I said, use some kind of dynamic programming here and do like kind of an exhaustive search type of a thing to prove that it's the correct answer, minimal answer. Instead of trying to find like a clever greedy algorithm, it's probably faster to do what I just suggested. Man. I'm gonna lay down again. These questions are so hard. Excuse me. I can see why this has so few submissions. Yeah, the questions we have to move things around and compare them to other stuff is those are some of the harder ones I have to say. They're generally pretty tough. Yeah, it's probably some kind of dynamic programming or something, but not obvious how to do it. Oh. Makes me think of the question we just did, where, yeah. Excuse me. Oh, wow. Oh, boy. Oh. All right. Okay. fell asleep again. Oh my goodness. I should probably stop here. Gee. This is quite a question. So I got stuck on this one. A lot of downvotes. Excuse me. So there really are only so many options for this. It's a pretty challenging question. I think the only options you really have are greedy algorithm of some kind, DP algorithm that's like related to the greedy algorithm, or a binary search where what you could do is try to find some number of moves that will succeed, and keep lowering that, trying to find a way to lower that number to the bottom, and then same thing, increase, basically binary search for the smallest number of moves that'll win, and then also search for the largest number of moves that can win. All of those options are not obvious to me as to how to solve this with that. But I think those are the only realistic possibilities, because it can't be a brute force algorithm, because it's 10 to the 4th is way too big for this solution given the time bounds. So it has to be either a recursion, memoization, or a T/TP, bottom top down or a bottom up approach, or it's got to be some greedy algorithm that works so you can prove will work. Or finally, there's excuse me, there's what's the word? A binary search that you can perform, some kind of binary search that also works. This is a good question, though. It's a pretty challenging question. Moving endpoint stones closer to the middle. Each time you make the interval smaller, the range of values smaller. I don't know. It's a challenging question for sure. I have to say, it's a pretty difficult one. Excuse me. Yeah, I don't know the answer. Not a lot of submissions. I don't feel too bad. It seems like a question that most people, if they got it, they probably fail it. So I don't feel too bad. Also, I fell asleep. Fell asleep thinking about it, I guess. So yeah, let me go. I'm just gonna stop here. Yeah. Just stop. Make this a part 1, and then tomorrow I'll come back and try to do more. Or later today, really. It's very late now. I don't know. Some questions are just a little bit harder than others, I think. Like the LeetCode hard questions are definitely, it's pretty typical that it takes at least a day, because they're just a lot harder. I think this one probably is like a pretty tough one given the submission rate. It's like a very low number of submissions as compared to some of the other medium questions. So pretty high acceptance rate though of the people who figured it out. But yeah, it's kind of hard to, when you have that many numbers, excuse me, I don't how to say it, like, when you have that many numbers, it's, when you have an array of numbers as the input, right? Of a lot of numbers you're working with. It's sort of challenging to go for like a DP solution. Well, it makes me think of sorting. Actually, sorting is kind of interesting because the number of possible states to consider, and so when you're thinking about sorting, is actually a factorial number of permutations. Sorting is like a kind of a special case of algorithms because it's there's a lot of research that's been done on it. That's the first thing. The second thing is that excuse me. If you were to try to use a greedy algorithm or I mean, I haven't really done much divide and conquer, which divide and conquer really is just like DP. Looking for optimal substructure, they call it. Sorting algorithms are kind of special in that you don't have that many variables to work with, or excuse me, you technically have a lot of variables to work with. You have like an n factorial sized search space you have to work through. It just so happens that the way sorting works is that like you can actually search that search space efficiently through all the permutations. This algorithm is this particular question is it's not really the permutation space, but it is sort of basically each endpoint there's potentially 1 billion different positions that endpoint can move to. Or 500 million or whatever it is. And there's 2 endpoints, so there's billion different options potentially for each state to move to the next state. State changes. And then from those options, I suppose there's another 1 billion possibilities, something like that. Not necessarily, but quite a few. So this search space is like very large, could be very large, I think. Now the question is how much of that search space is just redundant, right? How much of that can be just skipped? Kind of what I'm thinking. A very interesting question. And then you also could approach this, as I said, like in a totally different kind of way where you can actually binary search on just the answers that you're trying to output. Which maybe that's what I need to do. Like maybe it's like a double binary search where binary search for the numbers I'm looking for, and then once I pick a particular number, it could be like n log n time to assert. So n log n log k kind of a thing. I'm not really sure. I don't know. It's a hard question. I don't know. Not hard, but it's challenging. It's challenging. It's not rated hard. It's just an interesting question. I don't see the answer immediately. I already fell asleep, so I slept on it a little bit. I have to keep thinking about it for a while. I don't know. It's a good question for sure. It's definitely a good one. Definitely a good one. Alright, I'm gonna stop there. Thank you for watching. I'll talk to you soon. Yeah, I try to solve questions without like just looking up the answers. What they call fluid intelligence, trying to practice that fluid intelligence. Which I think is maybe kind of a silly thing, quite frankly. It's if you already know an answer, like I wonder sometimes if that's something I should be doing. If that's really all that valuable. To sort of quote unquote reinvent the wheel all the time. I don't know. I'm not sure. I actually don't know. I don't actually know. I don't know if it's maybe just a waste of time. I do like to challenge myself though. That's pretty good. Like I like to try to solve something I don't know the answer to see if I can think up something I haven't thought of. Maybe find something that I already know that could be useful. Yeah. I don't really know. I kind of wonder sometimes if it's just like maybe I should just be looking up like answers to things and memorizing those things, using the tools at my disposal that I have. I don't know. But anyway, I'm gonna go. Thank you for watching. I'm gonna rename this with yeah. I'll stop the stream here. All right. Take care.